Analysis Lab, we recently had human resources come in and do a job reclassification, and so we got to choose our own. So I decided I wanted something sort of more modern to reflect today's rapidly moving and organic social media framework. So now I'm the Senior Associate Deputy Vice President for Client-Side Geospatial Engagement of New Digital Strategy at the University of Vermont. So you're welcome, everyone. So let's get into mapping buildings in Vermont here. And the real reason we're able to do this is that we've got this plethora of Lidar. And so hats off to Mike Briette and sort of Team Lidar in Vermont that have helped put the funds together to pull this off. This is a screen capture from the the United States Interagency Elevation Inventory, and so this is administered by NOAA, but it's showing all the LIDAR collects within the Northeast. And as you can see now, within Vermont, we're completely covered. Doesn't mean we have complete LIDAR coverage yet, but it's planned and on the way. So this is really exciting, and exciting all throughout the Northeast here when you look at the amount of coverage. So this is just fantastic stuff. So for today, what I'm going to show you is an example of how we've built an automated routine, so it's an entirely automated routine, to extract buildings from a combination of LIDAR and imagery. So for the area of extent, I'm going to be focused on the 2014 sort of quote-unquote Chittenden County LIDAR that's available, which actually extends sort of up this area here. And so these are each one of those LAS tiles, the LIDAR tiles, and this is the area focused. Okay, so this data has been processed, and I sent out an email to the Vermont GIS listserv prior to the start of the webinar that gives you a link where you can download this information. So please keep in mind this is for evaluation purposes at this stage, so use at your own risk. So once again, let's dive into why this is possible. First of all, we've got great high-resolution imagery. Okay, these are the 2013 leaf-off orthos. Leaf-off orthos, great for building mapping because we can see through all the deciduous trees. And then what's even more important are the LIDAR data. And LIDAR data give us the height of features. And imagery alone is just not enough to do automated building extraction. And so we're able to build these advanced, what we call rule-based expert systems that use object-based image analysis techniques. If that sounds fancy, well, that's because it is. And we're able to do things like extract buildings. Okay, so this is the example of the building output that we have right now for this area in Chittenden County. It's not entirely perfect, but you overlay it on the data, and I think it's pretty darn good. And especially as you zoom out, it gets even better, right? So it looks really, really great at 1 to 24,000, looks still pretty good down to 1 to 2,000. It's when you get to sort of 1 to 400 or 1 to 500 that we are now that you're able to spot errors. So as with all data, just don't zoom in too far. And let's take a look at those buildings on top of the imagery here. Okay, so once again, pretty nice stuff. And we'll come back to this at the end and look at some of the examples. But for right now, I'd like to walk you through the process and give you an understanding of how this works. So Leslie sent me an email earlier in the week saying, are you all set for the webinar? And I'd been traveling last week, and I'd completely forgotten that I'd signed up to do the webinar, so I didn't have a heck of a lot of time to prepare for this. And what I needed to do was completely go from data prep, so take the LIDAR and imagery, develop the algorithms to extract them, process this on our high-end servers, and get to the point that we had buildings. This was really nice because it gave me a time crunch to see how quickly I could operate in. So data prep here took about 6 hours, so Taylor Engel on our end handles that. Algorithm development, leveraging existing routines we've done for other development mapping projects, took around 3 hours, and then processing on the server took around a little bit less than 3 hours. So basically, you can do this in a really long day. At UVM, we only work, really 2 to 3 hours a day, so this is about a week's worth of work. But for those of you that work harder, this is something that can conceivably be done in a day. All right, so let's dive a little bit deeper into the LIDAR data here. So here's a LIDAR point cloud. A lot of you have seen the point clouds, right? XYZ locations also have LIDAR intensity and point return information. What we do is we process the LIDAR data from the absolute elevations to what you see in the next slide here, which is the normalized elevations. Okay, so we normalize the height of all points relative to the ground for feature extraction, and that's because we want to know the height of things relative to the ground. So like I said, LIDAR data has more than just the XYZ locations. It's got intensity information. That's what allows us to do some of these beautiful color composites that you see here that resemble some cases, orthophotos. So in addition to that, we also run some Lidar point cloud classification algorithms. They rely on the return information in the Lidar point cloud, which is what you're looking at here, and that allows us to improve upon the vendor point cloud classification. So typically the vendors are going in and they're classifying the ground features from the above ground features. They might identify water. In some cases they'll classify the noise points, things like that. So in this case we ran an automated routine to separate out the buildings from the tree points. And these routines work really well, but they're not perfect. And so we'll take a look and zoom in, and we have this particular building here. Okay, this building is one that's clearly visible in the Lidar. Okay, and then we go to the point cloud classification in the next slide. Okay, and we can see that that cyan color is the color for buildings. Red means it's something that's tall, that's not tree or buildings, and the dark blue there are the trees. Okay, so here you have an example where the point cloud classifier is not exactly correct, and you see these small errors in other buildings as well. So there's two issues here. One is that the Lidar point cloud classifiers have some problems. The other thing is none of you out there want Lidar points, right? Lidar points classified as buildings don't do you any good. We can't just give you 150 gigabytes of Lidar points classified as buildings and say go on and make your decisions. You want Lidar polygons, and that's where the automated routines come in. So the automated routine that we ran for this is a rule-based expert system. Okay, coming up on your screen here, it's showing the code. So this is about 32 pages of code. Now we didn't write all this within that single 3-hour time period, right, when I was rushing to get this done. This is based on previous projects that we've done over the years. So we've constantly updated and refined these procedures, and now we're at the point in Vermont where we've got great Lidar where we can apply these. So now I'm going to walk you through this process of automatically extracting buildings from remotely sensed data. So first slide here, this is our color infrared leaf-off orthophotos. These were acquired in 2013. Okay, wonderful data, 15-centimeter resolution in Chittenden County. Really, really nice stuff. So we start with the imagery. We also make use of our Lidar data. And we're making use of our Lidar data as a point clouds. Those are loaded into the system. And then also raster surface models. This is what we call a normalized digital surface model, or NDSM. It represents the height above ground. Now what's really interesting about Lidar data is each one of those points has return information associated with it. And so in trees, we get a lot of returns. It hits off the top, hits off the middle branches, and hits off the ground. But buildings, it's just going to hit off that roof. It's not going to penetrate the roof. So we can filter those points and generate something that we call, in our case, just a normalized digital terrain model. But this is essentially the lost returns, the height of the lost returns above ground. And in this case, you'll notice that a really nice job in highlighting buildings. There are still some trees in there, either portions of trees. So in the case of deciduous species, these are the thicker branches or their trunks, and then we're also seeing some of the evergreen species there, which of course keep their needles on during the winter, and Lidar has a harder time penetrating. This is a really valuable layer because it removes a lot of the non-building features out there. The next step then is to begin to create something that we call image objects. Okay, these are polygons. We apply a segmentation routine to identify all the things that could be buildings. And so we're using a simple height threshold here, and we're saying create polygons off of these things that look tall in this surface model. Now, unfortunately, that includes some trees, some sort of things like utility lines, and then of course the buildings that we're actually after. So then we resegment those objects, so cut them into finer scale objects or more objects based on segmentation algorithms. Once we have these separated, and we're separating them out based on their properties in the Lidar data and in the imagery, so making use of all this information out there. And then we can begin to classify these features. So the first thing that we do is say, what are things that definitely look like buildings, right? So these are things where it's clearly a building in the point cloud, right? It's got very little difference between the first and last returns in the Lidar data. It's got low NDVI, meaning that it looks like a man-made feature within the imagery, all of this stuff. And then classifying the trees as well. So all those yellow things you see here are stuff that look like they're definitely buildings. And then the sort of greenish, bluish color there, those are things that we definitely think are trees. And then we've got these orange and purple things, which are things that we're less certain about, and we need to refine them. Okay, so we keep stepping through this process, and we're building knowledge over time. And so these are expert systems that are sort of learning upon themselves, right? Much as you as a human would approach this particular project. And eventually we get to the point where we have the buildings of interest. Okay, so we've narrowed down our data set to focus on the buildings. Now these buildings are objects, and they're kind of, you know, that's a good classification, right? You can see here we're missing a small portion of one building, where we've got some overhanging tree canopy which mess things up, but overall we're really mapping these buildings very, very well, but they don't look fantastic. So we have to begin to refine them in order to make them cartographically pleasing and realistic, because there's nothing more that GIS people hate than bad-looking data. So we have to take these objects, which are inherently sort of a raster form, and then we have to vectorize them. So up on your screen here, you'll see our red objects, which are our buildings, and then you'll see some yellow outlines surrounding them. Those yellow outlines are the vector representation of those buildings. And like I said, the problem is that because the LiDAR data is not always smooth along an edge, it sort of trickles down the sides of buildings and trees, we end up with these very jagged edges. So we want to try simplify then orthogonalize these buildings to make them appear more realistic for our GIS work. So the first thing that we do is we simplify those buildings. So you notice a transition there in which the vertices along those buildings have been removed. And we're still doing these routines within our automated framework. Okay, I tried to do this in ArcGIS. I started the process 2 days ago, and it's still running using their building simplify routine. So these are things that just don't lend themselves to standard GIS workflows when we're dealing with hundreds of thousands of vector data, as in this case, right? So we simplify it, and then we do another routine, sort of a squaring routine, to orthogonalize the buildings. Now this has some benefits. The buildings begin to look more realistic, but this is also, I think, the most problematic part of this workflow, because it does try to sort of square up these buildings. And as a result, it can distort their orientation sometimes and distort their edges, especially when we're zoomed in really beyond the scale at which the data are accurate, in this case, which is 1 to 500. So that's the process. We've ingested all of these data into this fancy object-based expert system. We've run this 32 pages of code across all these dozens and dozens of LAS files. For each one of these LAS files, we've kicked out these building footprints, and now let's see how they look by bouncing around through some examples. So here we are looking at some of the data overlaid on top of the ortho photos here. All right, you're going to notice a few things. You're going to notice that we do a very good job at finding buildings, right? And then you're going to notice some strange things, right? The orthogonalization routine will do things like it'll square up smooth features like water tanks and things like that. You're also going to notice some cases things that look like errors. Sometimes those are errors. We're picking up things like false trees out there. Other times it's actually new construction that shows up in the LiDAR, and I'll show you some examples of those because the LiDAR is just a year newer than the imagery. So we're going to keep bouncing around. Here's another area. In this particular graphic, what we're looking at here is a combination of the building outlines in red, and those are combined with the E911 points. These are just all E911 points, not just those filtered for buildings, the E911 points in the green dots. So you can see what's really valuable about doing this type of mapping is that we're able to pick up buildings that are not in the E911 data, right? And so I think my next step for this is actually going to be incorporate E911 and buildings together and use that information to hopefully perhaps tease out some areas where we might be picking up some trees that sort of resemble buildings but are really far away from E911 points. Okay, another area here, we'll do the same thing. I think this one's kind of compelling because we've got some rooftops here that actually sort of don't necessarily look like normal impervious surfaces. They kind of have this purple color. And once again, you can see these E911 points out there, and not all the buildings are available in the E911 data set. So we have this ability by doing 3 hours of processing to comb through massive amounts of data and find features and structures that we might be missing from other things, in addition to representing them like polygons. Let's move to some more urbanized areas here. You can see some more examples. And once again, I'll point out we're doing a very good job at finding the buildings. And then you'll find these buildings which have somewhat complex structures. So sort of the U-shaped one over on the left there. And you'll see the edges get a little bit jagged sometimes, right? So the orthogonalization routine is distorting the actual shape of that, right? If we were to digitize that, we'd probably make some straighter lines, even though it's probably valid to have some jagged edges in there. Okay, so these are some of the challenges we have in automated building extraction. I would say that it probably gets us, 95, 97, 98% of the way there, but getting that other 2 or 3%, that really requires a lot of work because we're talking about manual editing. So the cost savings of automated feature extraction is massive, but if you want things to be absolutely perfect, then you're talking about at least some level of manual editing. So the next slide is interesting. So as I was scrolling through these data, I noticed something. So in some cases in these sort of industrial areas, we're picking up things like shipping containers or high features in these lots, right? So they may not necessarily be buildings. But right in the middle of your screen here, you're seeing something that looks obviously like a massive error, right? And this was of great concern with me. So I went back through and said, oh my gosh, how did I mess this up? Without just doing the simple thing, which would have been to turn off the imagery. And if I had done that, what I would have found is if you look in the Lidar data, there's actually been brand new construction there. So the routine was actually good enough that it, even though the imagery didn't show the building, it relied so much on the Lidar data that we're able to accurately extract that building. So there's a lot of value there in places where a human might make mistakes. I think this routine actually even provides some advantages. So hopefully that gives you a quick overview about the plans for building extraction. We've got a little money to do this at UVM, and we're trying to see what sort of resources we can leverage to make this happen throughout the state. If you're interested in downloading the data that I showed today for evaluation purposes, I'd appreciate any feedback. And by any feedback, I mean sort of a quick email saying, Jarlath, I downloaded your building data and it's awesome. I've never seen anything else this good in my life. That's the kind of feedback that I really want. But if you have other feedback, we'll accept that as well. Okay, so this link here, go.uvm.edu/1-50, that's O is in the letter lowercase, and the number 3, okay, and that'll give you a shape file. And you can download that, play around with it. Keep in mind it's not all of Chittenden County, it's only for those areas which were included in the LIDAR that was flown in 2014. So Leslie, that wraps up the formal presentation, and we can turn it over to any questions.
Okay, great, thank you. I also want to mention, in case people haven't noticed, I sent out a few messages via the chat feature of GoToWebinar, one of which I didn't really notice was the link to this webinar to sign up for the webinar, so ignore that one. But the second one I sent is this very link that Jarlath was just showing to the data, the Chittenden County data. So you have it there as well. So now is your chance to send questions. We don't have any yet. The ones that I had gotten previously were, I'll mention also, were about whether your PowerPoint would be available for download. And I assume that you'll send me that after we're done, and I can post that on our website.
Yeah, I'd be happy to, Leslie, with the normal $5 fee for each download. Is that how we're doing things?
Oh, yes. That was just I'm going to have to ask people to actually mail those $5 bills to you, but...
That's a joke, everyone. I'm just in a little bit of a snarky mood because it's our holiday party today, and I'm starving myself for the catered meal that's arriving at 4 p.m.
Nice. All right. I'm going to try making you organizer so you can just look at the questions directly.
Okay, great. Thanks.
Big warning here about how you can override the access by the other one.
That's right. I see the question box, so let me see. Download presentation. You answered that, right, Leslie? Do you still get rounding of some building features due to tree returns that overhang buildings, and how do you address these? So in that particular case, we can have portions of buildings that do get missed if they are under tree canopy, and that typically happens if we've got extremely thick branching of the trees so that it's messing up the LIDAR returns. If the branching isn't that thick, or if it's not a coniferous and the LIDAR signal can clearly get through, we can map the buildings under the trees. And as you see here, I'm not displaying any of the leaf-on imagery, but we're getting all of these buildings here, a lot of which are almost entirely covered by tree canopy in the summertime sometimes. So we're able to do that thanks to the return information within it. So Jonathan Croft said, is there a project underway for UVM Sal to process the building footprint for the areas of existing LIDAR? Sort of, Jonathan. So the reason why we're able to do this is thanks to, what really amounts to probably like, I don't know, probably like $1.8 million in funding for projects outside of Vermont, where we've had to go through and do land cover mapping, and so we've developed and refined these algorithms over time, and now we're trying to bring them to Vermont. And we've got about $5,000 a year to do sort of like a little bit of LIDAR processing and land cover development in Vermont. So we're hoping to start rolling these things out now with this Chittenden County and then the Addison LIDAR to do these other areas. But if anyone has spare change you found under your couch, in your car, what have you, and you're interested in sending your tax-deductible donation to the Spatial Analysis Lab Building Development Fund, we would appreciate it. And I think really the big thing that we want to consider here that will not be addressed in the automated processing, there's going to be some errors. And with some investment, we could really improve those errors by sending our map monkeys here at the Spatial Analysis Lab to comb through and fix up this stuff. And I think that could rather dramatically improve the quality of these data. Other questions about old foundations or cellar holes. So as long as those things are not taller than really sort of like a couple meters, right? So we sort of use around this sort of like 10-foot threshold for buildings. Those are not going to get picked up. We could look at building a separate automated routine to find those if someone was interested in funding that type of work, but they're not going to get picked up. What would it cost to process the entire state? Yeah, so I think this is a really good question, and once again, it depends on what type of accuracy and quality we want. So if we're just talking about end of 2017, all of our LIDAR shows up, we just want to take the algorithms we have and pump it through, right? That's data processing, some algorithm tweaking because each LIDAR data set is different. So you're probably talking about, maybe probably sort of like the $10,000 to $20,000 range in terms of sort of labor and processing, not including whatever overhead our good friends at UVM might want to add to that. But I think you want to add a manual component to that, right? And that's really determining on what your specs want to be. But you could imagine going from anywhere from taking sort of a $15,000 project and depending on your manual edits, making that a $30,000, $40,000, $50,000, $100,000 project. And then of course, if you looked at doing this straight up as a manual method, right, if you take a look at some of the very, very wealthy counties throughout the United States that do pay for planometrics, right, these are single counties that are sometimes paying $200,000, $300,000, $400,000 every time they do a remote sensing data collect just for planometrics. So we've got considerable cost savings here, and I think once again it comes back to the fact of what level of detail are people comfortable with, right? And you may decide that a product like this is good enough for statewide analysis, and much like the orthophoto program, individual urban areas could buy up for sort of improved buildings. Someone asked about how would you compare and contrast this approach with traditional planometric mapping methods. That's a really good question. Nothing ever beats a human, right? Humans do such good jobs. Unfortunately, they're extraordinarily expensive, right? And you sort of see that you that have sort of run any numbers from the buy-up program for the ortho project. If you look at the numbers for what it costs per mile for planometrics, right, for some areas you can get into the 6 figures pretty quickly. So with this we can do things very, very accurately. We can do it quickly, but it's not going to be perfect. And we can make improvements on it through some manual editing, but we're never going to make every single building as good as if a person had used it. So software for this is another question. So there's a lot of different software packages we will use. On the LiDAR processing front, we use Scalgo and LAS tools. On prepping the imagery and mosaicing, getting them all ready, we'll do a lot of stuff in ERDAS Imagine for data general visualization. We're using ArcGIS. And then the bulk and really sort of the heart of it is the cognition network language, which is a programming language otherwise known as CNL, cognition network language, which is in a software known as eCognition, a bit of a niche software but really powerful. And the power behind that is not only being able to build those algorithms, but being able to distribute those to multiple processing nodes. So when we're processing this, we're doing it LiDAR tile by LiDAR tile. Each one of those LiDAR tiles goes out to a processing core. Each processing core needs around 8 gigs of RAM. So we're running about 20 of these tiles at a given time. So this is why you need not only the software and the know-how, but you need these high-end workstations that have sort of over 200 gigs of RAM to be able to do something like this. So that's where a lot of the cost goes, right? You have a computer that costs you maybe $20,000 to $30,000 with all of those. Whenever we call Dell support with an issue, they think there's an error because we tell them, they look at the system specs and they see 512 gigs of RAM on a machine and they think that it was a typo, but no, we're the people that instead of buying a car bought a fancy workstation. So Leslie, I think I went through all of the questions.
Yes, I think you're correct. So everybody, this is your last chance to send in a question. Otherwise, we're going to let Jarlath go.
Yes, and like I said, please download this, take a look, and welcome any feedback. Once again, definitely know there's issues. One of the things that I did not implement with this was a road center line check, so we're actually picking up some bridges, although of course this also points to the fact that you could use a similar technique like this with roads to develop an automated bridge mapping routine, right, all those things. Oh yeah, one last question we've got here. What do you think the smallest structure size capturable with this technique? We can get some pretty small stuff. I mean, we're talking a couple meters on a side, right? So really low square footage. There are trade-offs associated with that, right? So as we decrease the minimum mapping unit, our chance of picking up noise increases. And so once again, that's a trade-off. I mean, if you look even in this particular scene here, you can see that we do have some buildings, we've got some portions of buildings, right? We're probably picking up, 90-something% of the buildings. You can see that we are also picking up some smaller buildings out there, but we do have to make a decision about what level in there. That's something that if there was interest in sort of funding on doing this at statewide level, right, you can devote resources to clean up and then you can map all those tiny structures. One thing I didn't mention is that we can also use the LiDAR data to assign LiDAR attributes to these buildings, right? So we can give you the mean and max height associated with these, and then for some of our other projects we've given people back actually true 3D buildings. So if those of you who are professionals and are using ArcGIS Pro as opposed to the amateurs out there on ArcGIS Desktop, right, very easy to display that stuff nowadays in 3D and do all of your line of sight and things like that. Let's see, here's another thing. Can ridgeline height roofs be worked into the algorithm to assist with alignment accuracy? Yeah, we've done sort of some fancy stuff like that in the past of partitioning roofs into sections for sort of solar panel analysis. A lot of the LiDAR we have in Vermont doesn't really have the point spacing. So typically in Vermont we're working on sort of a couple to a few points per square meter. Really, in order to be able to do that stuff well, you want LiDAR that's operating on 10 to 20 points per square meter. So the answer is yes, but probably an algorithm like that just wouldn't be very successful in Vermont due to the LiDAR and then also due to the complexity, right, where we've got a lot of trees hanging over the buildings. And I think that might really be the end of the questions, Leslie.
Okay, great. Thank you, everyone. In case you didn't hear me say it before, this webinar was recorded, and it will be posted at our YouTube channel early next week. So if you're not sure how to get to that, you can either just search for Vermont Geospatial on YouTube or go to the front page of VCGI's website, and you'll see a link to our YouTube channel. I will also, we also have an event archive at our website, and there will be, and there's a webinar section of that, and there will be a link to Jarlath's presentation, his PowerPoint presentation on the event archive page, which probably you can find. And I think that's about it. Jarlath, if you could stay on for just a second after I shut down the webinar, that would be great.
Sure,
Thank
be
you,
happy
everyone.
to. Thanks, everyone. Thanks, Leslie.